Hello everyone, I'm Mingyuan from McGill University. Today I'm talking about our work, A Tale of Two Erasure Codes in the Hadoop Distributed File System. This is a joint work with Mohit Saxena, Mario Blaum, and David Pease from IBM Research Almaden. Nowadays, the global data is growing enormously, and we have seen a data growth rate of 5x to 6x over the past 5 years. And this trend will likely to continue into 2020, where we are expected to reach 40 zettabytes globally. So if we look at the big data stack, back in 10 years ago, we have when the Google file system is first introduced, the three-way replication is the standard method to provide data reliability. However, this scheme ended up with a storage overhead of 3x. Nowadays, because of the storage overhead pressure, most of these systems has transitioned to Erasure Coding to provide a low storage overhead. And we have seen a lot of work going on and adopts new codes and new coding techniques to bring storage overhead down to between 1.4x and 1.5x. This savings for sure saves a lot of millions of dollars for storing data in capital costs. So before I go into the details, I will first give some background of Erasure Coding. So originally with three-way replication, every data block will have 3 copies in the system. Now with Erasure Coding, each data block will only have 1 copy in the system. And I will give example of Reed Solomon 1410 code developed at Facebook. So here, this scheme will group every 10 data blocks into 1 stripe, and then compute 4 parity blocks from these 10 blocks. And the storage overhead here is defined as the total storage, the ratio of total storage to data storage is 14/10 equals 1.4x. When a failure happens, this scheme needs to fetch 10 blocks over the network to one place from the remaining 13 blocks to recover the lost block. And this had bring up 2 problems. One is the latency problem, commonly known as the degraded read problem. And also there is a throughput problem caused by this. It's known as data reconstruction. I will elaborate these 2 problems in the next couple of slides. First, let's take a look at the degraded read. Degraded reads happens when a client reads a block. So when you read a block, you have a chance to get a read exception because of software errors. For example, the data node you are touching is being updated, or the disk you are getting to is having too much traffic and cannot service new read requests. Also, some hardware failures and errors will also cause degraded reads. When you get a degraded read, when you get a read exception, you will need to fetch other blocks from other data nodes across the network to recover that unavailable block. This for sure incurs extra latency for this read request. The second problem is known as the data reconstruction problem. It's commonly caused by disk or node failures. And in some cases, when you're decommissioning nodes, this will also happen. When we have a failure in disk or in node, the system will detect this failure and launch a MapReduce reconstruction job. The purpose for this job is to read extensively from the system and fetch the blocks and recover all the lost block on that disk or node. According to the current data, a typical production cluster in Facebook contains a few thousand servers, and the new data coming in is at a rate of 500 terabyte to 900 terabyte per day. And we will expect a failure of over 100,000 of blocks every day. And this translates to a reconstruction traffic of 180 terabyte per day. This traffic will impact the foreground tasks in 2 ways. First, it will share the network bandwidth with the foreground tasks. Second, when a disk or a node is being reconstructed, all the reads to the blocks on that disk or node will also be degraded. So we look at all the existing production system. Most of them use a single erasure code. For example, the Facebook and the Google are all using Reed Solomon codes. And you will see here this graph, the x-axis is the storage overhead. The y-axis is the recovery cost, which is the number of blocks need to be transferred over the network for recovering one block. And here you'll see the two erasure codes used in existing system will have inherent trade-off between these two dimensions. So in this work, we want to develop a technique which can achieve lower recovery cost as well as using less storage space. So we start by first take a look at the workload data access skew, where we have 5 workloads, 4 from Cloudera customers and 1 Facebook workload. And the x-axis here is the file ranked by decreasing access frequency. The y-axis is the file access frequency. As we can see, both in log scale. As we can see here, only 10% of the data gets the majority of the accesses. And then the majority of the data is code, and 90% of them are just accessed for a few times. Note here, it's all log scaled. So motivated by this access skew, in this work, we propose to use 2 erasure codes instead of 1. We use a fast erasure code to code hot files, which provides low recovery cost. We also use a compact code to code the majority of the code data, which gives us overall low storage overhead. With the observed access skew, we expect that we can get the best of the both codes. We implement this idea and design our HACFS, which is the Hadoop adaptively coded file system. For comparison, originally the HDFS will triplicate all new files. When new files become write code, it will use the erasure code to code it. In most cases, it's a Reed-Solomon code. In our HACFS, we keep the 3-way replication for new files the same. When a file becomes write code, we subclassify it into read code and read hot files, and use the compact and the fast code accordingly. Here are the popular erasure code families that have been either adopted in production system or actively being researched. In this work, we apply our adaptive coding to the product codes and LRCs. Both are having a very low recovery cost. I will be mainly using the product code, for example. So here I show you a fast product code, which we call a 2x5 product code. This code will group every 10 blocks into a 2x5 matrix and compute horizontal and vertical parities from these data blocks. Here, the horizontal parities, for example, P1 is computed by taking the XOR of the data blocks on the same row. So P1 is the XOR of D1 to D5. Similarly, the vertical parity is computed by taking the XOR of the data block on the column. So P3 here is the XOR of D1 and D6. Altogether, we add 8 parity blocks to every 10 data blocks. And this comes at a storage overhead of 1.8x. After encoding all of these blocks, data blocks and parity blocks are distributed to different nodes to provide fault tolerance. This code, when we have a single failure, we have 2 choices to recover it. We either take the column or take the row. And we will choose the column here because we only need to transfer 2 data blocks to recover that. On the contrary, we also have a compact code which uses larger matrix to get lower storage overhead at the cost of higher recovery cost. Here we use the 6x5 product code, which can effectively reduce the storage overhead to 1.4x at a recovery cost of 5. We put these 2 codes in the trade-off space we've seen before to compare these 2 codes with existing single-coded systems. So here we see the compact code on the left and the fast code on the right bottom. So with a specific workload, HACFS can achieve a point within the rectangle bounded by the 2 chosen code. When the code data accounts for the majority, the storage overhead of HACFS will approach that of the compact code on the left side. when hot data is accessed more frequently, the HACFS will achieve a recovery cost close to the fast code. So the optimal performance point is on the left bottom side of this rectangle, which provides the lowest possible recovery cost and the storage overhead given the two codes. And the data access skew observed from real workloads will help us to converge to this point. Furthermore, we also set a storage bound, to make sure that the system always stay within a particular storage overhead. For example, we can choose 1.5x for this case, which is used in the Google Colossus production system. And to bound this storage, we need 2 extra coding methods to provide for support. When the system is over the bound, we develop a new coding method called Upcoding to bring some files that has been previously coded with Fastcode to compact code. In this sense, the HACFS first lists all the files that are coded with Fastcode, and then the system will upcode these files to compact code in LRU orders. We named this operation as upcoding because it's getting the recovery cost up. Similarly, but less likely, we also have a downcoding operation. This happens when the system is way below the bound. We'll convert some compact code to fast code. So here I will show the upcoding example for product codes. The goal here is to merge 3 2x5 fast product code to a single 6x5 compact code. And as we can see that the data blocks on the row stay the same. So the horizontal parities do not require recomputation. We only need to update vertical parities. And as noticed, the new vertical parities can be effectively computed by taking the XOR of the old vertical parities at the same position. So when updating the parities, we do not need to read data blocks. Overall, all the parity updates can be done in parallel and in a distributed manner. We have implemented HACFS with these 2 codes, the product code and the local reconstruction code. We also develop efficient up and downcoding operations for the other 3 popular codes as well. For evaluation, we implement HACFS on top of Facebook's HDFS. It has 3K lines of code spanning across 3 new modules. One is to monitor the file system state, one applies the adaptive coding state machine, and one providing the coding support for product code and LRC. We evaluate our system with 5 workloads, 4 from Cloudera customers and 1 from Facebook. We set up a cluster of 11 nodes for our experiments. So here we are particularly interested in 3 metrics. The first is the degraded read latency. This comes when a foreground task reads a block that is not available, and the recovery time will factor into the read request. And this is mostly caused by the software issues. For this experiment, we inject faults by deleting a specific block in the system and then read this block to trigger this degraded read. And the second metric we are interested in is the reconstruction time. This happens when the hardware failure happens and the system will schedule MapReduce job to recover the lost data. For this experiment, we inject faults by taking off the entire disk and inform the system of this failure. The third dimension is the storage overhead. For sure, we want to provide bounded storage overhead to the system administrator. So first, we'll take a look at the degraded read latency. Here, the x-axis is the storage overhead. The y-axis is the degraded read latency measured in seconds. Our cluster during this experiment is heavily utilized. There are several MapReduce jobs running in foreground in addition to this recovery operation. And we first measure the numbers for 3 production systems. All of them are single-coded systems. Facebook and Google using Reed Solomons, and Windows Azure storage is using local reconstruction code. Then we put the HACFS implementation with product codes. The compact code has a similar storage overhead of the Facebook implementation. And the Fastcode span to the right bottom side of this rectangle. We use the 1.5x as the storage bound, which is also the storage overhead provided by the Google Colossus. So here we show the two HACFS implementation. The blue box is the HACFS implementation with product codes, with a bound of 1.5x, which is the Google Colossus storage overhead. The red box is the HACFS implementation with local reconstruction code, bounded by Facebook's production system. We see that although we have enforced a tight storage bound, we always have a recovery cost lower than the compact code we chose. And the CC1 is getting the best of both code. It's getting low recovery costs as the fast code and also the low storage overhead of the compact code. This is because its majority of its access go to the hot data and the majority of its data is very cold. So next we take a look at the reconstruction time. And here the y-axis changes to reconstruction time of hour. The system will code most data with compact code. That's why we will have low storage overhead as observed. However, when we lose data, we also lose majority of the files coded with a compact code. And the compact code has a higher recovery cost. So as a result, we expect that when the storage overhead is low, the recovery cost, the reconstruction time also approach that of the compact code. Here, the best case is the CC3 and CC4 because it has fewer code data compared to other workloads. On the contrary, the CC1, which is very close to the compact code performance, has the majority of data in the code state. Here we show the system-level comparison of our two HACFS implementation compared with 3 existing systems. And this shows the percentage improvement averaged across all 5 workloads. We implement HACFS with product codes to improve existing Reed-Solomon-based systems. As we can see in the upper table, our HACFS PC can effectively reduce the cost for 2 recovery scenarios without incurring much extra storage overhead. And we also implement HACFS with local reconstruction code to improve existing LRC storage-based systems, which is the Windows Azure storage. As we can see in the lower table, the degraded read latency is also benefit a lot. And the HACFS LRC does not just lose 5% of the storage overhead for achieving the 20% improvement in degraded read latency. Overall, HACFS is a general methodology which can better exploit the strengths of each individual code family. And the product code here is better for recovery, LRC is better for storage overhead. However, if you compare a HACFS PC, which is optimized for recovery, with LRC, which is optimized for storage overhead, you may not have a fair comparison. So that's why we lose 10% storage overhead here. In conclusion, most of the existing systems we know are using single erasure codes. And we provide a general methodology which uses 2 erasure codes to effectively trade off in our adaptive coding rectangle. We have implemented HACFS with product codes and a local reconstruction code. We develop efficient downcoding support for these 2 codes. And with our experiments, we show that the HACFS can explore its workload characteristic to better review the strengths of each individual code families. Here I conclude my talk, and thank you for listening. We also have a poster in the poster section. If you have any questions, you can come by and we can chat. And I will be happy to take questions.
So Brent Welch at Google. So I think you're trading off reliability for recovery time. So in the product code that you had pictured, for example, it's not 3 fault tolerant. but you're comparing it against 6.3 encoding, which would be 3 fault tolerant, or a 1410 encoding, which is 4 fault tolerant. So are you sure in your real life work, are you actually comparing codes that have the same redundancy?
The 2x5 and the 6x5 protocol are both 3 tolerant. And they are the same as the LRC chosen in Windows Azure and the 9.6 used in Google Colossus.
Okay, oh no, that's right. Yeah, so the bottom, that's what the bottom right corner is for. Okay.
Yeah, okay. The global parity sort of.
The global parity. Okay. All right, thanks.
Thanks.
Oh, well, I'll let.
So my question, Konstantin Shvachko, one disk. My question about whether we lose redundancy using Erasure Codes. So in HDFS, we have a block placement policy, right? That takes into account racks. And in this case, if you choose 10 blocks from the same data node, then you lose one data node, you basically lost all the data that corresponded to those blocks. I mean, is there any thinking around that?
In the three-way replication, the replicas are supposed to stay on different data nodes. It's the same as for erasure codes. So when you after encoding, your data blocks and the parity blocks in the same stripe will be striped across different data nodes. So you won't lose a single machine and lose 2 blocks in the same stripe. Thanks.
Hi, I'm Rashmi from Berkeley. This question is related to the first question about reliability. So you said that it is 3 failure tolerant, right? But it is 3 failure out of you have 6x5. So when you change the matrix sizes, so you are 3 fault tolerance, but it is 3 out of 30, right? So the reliability is decreasing as you go from non-compact to compact.
Yes, I agree. In our paper, we have the MTTF measurements for these 2 codes. And we have shown that it's no worse than the 3-way replication for sure. It's comparable to LRCs and Reed-Solomon, I believe it's 9.6.
I see. Okay. Yeah, I will look at the paper.
Okay, thanks.
The other question I had was, what's the intuition on how important the fast recovery code is for a hot read file? I mean, do you have any trace data that shows that you're actually reading hot files in degraded mode often? Not because of disk recovery, but just for, well, background maintenance, I guess. Because if you've got too much cold data, what's going to dominate is just the recovery of the cold data.
In the workload access Skew we have here, most of the code data is only having one read. We think that's the file is created and read once and then stay there. So still the majority of the access is like 90% of them, or at least 80% goes to hot files. Yeah. Thanks.
Right.
Thank you.